Hey, welcome to part 6 in Models of Growth. And we've been looking at the exponential function. And of course that involves what? Exponents. Come up here. Exponents or powers or indices. So I think it might be time to go back and make sure we can do some work with those indexes, indices and exponents and stuff like that. So around the screen I've got a little puzzle for you. Can you identify the different types of expressions there? And well, they're all exponential expressions, aren't they? But they fall in different types, do you think? You might have a look at the colour coding. That might help you. So maybe pause the presentation for the minute and see if you can identify the different ones going on there. All right, well, let's start now. I don't know, I reckon 5 to the 0 and 7 to the 0 would be one little group there, and that's bringing home the idea that a to the naught is 1, with the proviso that a, the base itself, is not equal to 0. All right, I wonder if you can prove that one. Okay, we'll have a look at that later on. What's the next one? The easiest ones to look at, I think. Maybe the two reds, 2 cubed and 8 to the 4th. That's just simply the definition, isn't it, of a to the n, where you've got some base raised to the n, and that means you're multiplying a by itself so that you have n terms. So 2 cubed is 2 by 2 by 2. Okay, notice it's probably not particularly correct to say a multiplied by itself n times, because a multiplied by itself gives 2 a's. You see the idea? So really it's a multiplied by itself, so you have n terms. What's the next most difficult one, do you reckon? Oh, I don't know, perhaps, what about the greenies? I don't know. Or the purplies. Let's do the purplies first, this one. 6 to the neg 2 and 4 to the neg 3. What's that introducing? That's introducing the idea of a negative exponent or power. A to the neg n is 1 on a to the n. Can you prove that one? We might have a look at some of these proofs later on, so that you're not just treating it like a set of rules. You actually get up close and personal with the maths there. And maths can be fun if you do that. Okay, what do you reckon is next? Well, I reckon some of these rational powers here, 3 to the half, 64 to 1/3, all of those. Let's look at the greenies then. Let's look at 64 to 1/3. Where's the other greenie? Oh, it's over here. So what's special about them? Well, the fractional power, a to the 1 on n, means the nth root of a. And can you prove that one? The nth root of a. And so what does 4 to 3 over 2 represent? Well, let's do the root part first. That's 4 to the half all cubed, or root of 4 is 2 cubed, which would be 8. We've got another rule in here, haven't we? Remember that one? A to a power raised to a further power is a to the product of the powers. And that's the rule I just undid down here to find the half power of 4 first and then cube it. All right, what about these other fractional powers then? What about this one up here, the blue one? What's another blue one? Can we find one? Or here's one down here. The blue ones. Well, what's special about those? Well, it's a bit hard to see, but this means the square root of 3, and it's not a perfect square, so you've got to leave it like that as that irrational or absurd expression. And down here, this is the 4th root of 5 all cubed. And again, this is not a perfect power of a 4 of any number, so that's an irrational number there, so it's got to be left. So they were special rational powers. I'm just better just make sure you understand rational numbers. Rational powers are ratios of integers. So they're fractions, if you like. Okay, you can think of them like that. All right. Okay, well, we got some more rational powers around the place. So let's have a look at them. I think we've got two sets left. We've got the light green here and the light green there. And what do you notice about them? Well, they're negative exponents, aren't they? So you've got everything happening there. Let's do this one. This would mean 1 over, because of the negative exponent, 2 cubed, which is 1 over, let's do the denominator here first, the cube root of 8, all squared, which would be 1 over 2 squared, which is 4. Cube root of 8 is 2. Okay, and this one down here, can you do that? You might pause the presentation, have a go. The negative power in here means 1 over 25 to the 3 over 2, which is 1 over, the half power is root 25 cubed, which is 1 over 5 cubed, 125. 5 by 5 by 5. Okay, let's look at the last two now. So here we have the orangey one, and up here an orangey one. And why do you think they are a special group? Well, let's have a look at this one. It's a negative exponent again, 1 over 5 to the 3 over 2. And this is 1 over root 5 cubed. And so that sets itself apart because you can't find the square root of 5. It's not a perfect square. So it's a irrational number there. You can't go further with it. Not exactly, because it's got a non-terminating decimal, non-recurring, non-terminating decimal. And this one is 1 over 3 to the 1/4, which is 1 over the 4th root of 3. Boy, haven't I messed up the page now. But I hope that's starting to bring back some of the rules for exponents, which if we're going to analyse models of growth where they are rapid, it's probably going to find, or the growth is rapid, or the decay is rapid, you're probably going to find the exponential function lurking in there on quite a few occasions. Come back, we'll just get rid of that. Come down and let's have a look at those rules now. So some screen clippings from Hayes and Harris publications there, so have their book handy by. Do you remember these? And we'll try to quickly prove them as well, so you're not just using a nonsensical rule, thing that you don't understand. Get up close and personal with maths. It's fun then. So a to the m by a to the n, you add the powers or indices. What does that? Why does that come about? Well, if you've got a times by itself, so you've got m terms, and then you times by a to the n, and a to the n is so that you have got n terms. How many a's have you got altogether? M plus n. Okay, and consequently this rule up here is born. What about the subtraction here? A to the n, up the top, so there'd be m terms, and a to the n down the bottom. And notice I'm suggesting perhaps there are less terms down there. If you start cancelling them out, etc., you will have left m take n terms, wouldn't you? If m in the top line is greater than n in the bottom line, so it'll be a to the difference because they would have cancelled. Okay, so that's another rule. What about we'll come and look at this one, I think now, after that rule, because here, a to the neg n, how would you get that? Well, let's take a to the m and a to the n, and this time, let's make there be more a's in the bottom line. So there'll be m terms here and n here. And when we cancel them out, let's say there's more of these. So it'll be a to a power here, m take n, but that will be negative, won't it? Because n was bigger than m. So what you'll have is a negative power means you've got a residual number of a's in the bottom line. That's where that rule comes from. A to the neg n means you've got a negative number of n's because of your subtraction, and they're in the bottom line. So the easy to remember algorithm or rule there is a negative power means the reciprocal, 1 over. But this is the proof of it, if you like, a little informal proof there, where you take that away and n is bigger than m, get a negative number, and what's the result? Why did that happen? Because all the a's are left in the bottom line. Okay, let's have a look at this one over here now. Now we can't have b as naught because we'd be dividing by 0, which is undefined. But if you've got a over b all to the n, what does that mean? It's a over b times a over b, n, so there's n terms here, n terms. So if we actually multiply all these fractions together, it's a by a by a, so it's just the multiplication of fraction rule, there'd be n of them, and b by b by b, there'd be n of them. So in other words, you can, if you like, multiply a over b by itself, so you've got n terms, or you can just do all the a's over all the b's. Okay, and the same thing here. A to the m all to the n means multiply it by itself, so you've got n terms. Okay, n terms here. So what's that? You're going to have a total number of terms of m times n. Okay, so here you've got a's. Each of these, of course, I might be skipping a bit there, is a by a by a, m times. M terms in there. So if you do it n times, it's n times this m, how many a's you've got. Okay, so think about this. It's interesting, isn't it, when you unpack it all. And the same thing over here. This is ab times ab times ab. So there are n terms here. So how many a's are there when you multiply just the a's together? It'll be a to the n and b to the n. Okay, not hard to see here. Oh, a to the naught. How do you get a zero power there, or exponent? That can't make sense, surely. You can't multiply a by itself, so there's 0 terms. How did that come about? Well, let's have a look at a to the m over itself. A to the m. Okay, so according to our rules, so there are m terms here and m terms here, you would have a to the m take m, which is a to the naught. Hey, well, using our rules, we don't want to go back on our rules because we established that rule over here. So if we're going to keep our rule for consistency, we've got to say, what is it when you actually work it out? It's 1. So to be consistent with our cancelling and our previous mathematics, we've got to call a to the naught is 1. Or just not bother with it and say it doesn't fit our usual definition of a to the m being a times itself, so the m terms. No, we won't. We'll go for consistency. Okay, so come back right up the top here. This definition here, or we're not there, where I haven't got it here anywhere, have I? A by a by a. That definition of a to the n falls over when n is 0, doesn't it? But we can develop the theory so that we accommodate this situation. And also this one. This a to the neg n is a difficult thing to interpret if you're using our definition up here, that a to the n is n lots of a all times together. You can't have a negative lots of a. So we've expanded this definition to be consistent with other maths and for the situation that came up when we did our rules. Particularly this rule here has given us a bit of a headache there, because if m is equal to n, you get naught, so we've got to consider that. And if m is less than n, you've got this negative exponent. Okay, so we're developing the theory, aren't we? And this is quite, this happens quite often in maths, where you have a basic a definition, and then as you work with it and develop the theory, it becomes a little bit different as we go. Okay, and here's another one. How can you have A times itself with 1 on n terms? It seems a bit strange. And the answer is, again, this is developing theory. If you wanted to say what number multiplied by itself n times gives A. Oh, by definition, that's the root of n, right? Times root of n, nth root of n. If you do it so there are n terms, this comes back to A, doesn't it? The square root of A by the square root of A is A. The cube root of A by the cube root of A. This is the definition of the square root and cube roots. This comes to A. So there we have it. The nth root of A times itself gives A. So, can you see that if you did 1 on n times, what would you have? You'd have n, 1 on n to the n which would be A. So this also, A to the 1 on n times itself, so there are n terms gives A. So by this definition, it must mean the nth root of A. How about that one? Now think about that now, so that if you had, let's do another one, A to the half by A to the half, adding the exponents, A to the 1. So by definition, these two little creatures, which are the same as each other, when times together, give A. So they must mean the root of A. Okay, A to the half would be the root of A. Okay, I hope you can see how that theory developed. Come right up the top. So this is our fundamental idea of A to the n, A times itself, so there are n terms. But gee, there's some modifications as we went through and the theory's developing. So think about that. Okay, let's go down and practice some stuff. And here we go. 2D1, just writing things as powers of 2, getting the idea of negatives. Can you write 32 as a power of 2? 1 over it would be that negative power. All right, pause the presentation, have a go at all of these. Might need a calculator for some of these. I don't know what your number work is like. Okay, let's look at the answers now. And there they are. So mark your work. Make sure you get them all right. Let's move on. And let's look at an example. Screen clippings here from Hayes and Harris Publications. Grab that book. Okay, so write as a single power of 2, 4 by 2 to the n. So what is 4? 4 is 2 squared. By 2 to the n, add the exponents, right? Okay, 2 to the m on 8. 2 to the m is already a power of 2. 8's power of 2 is 2 cubed. The single power of 2 is subtract the powers or exponents from the a to the m on a to the n rule. Okay, let's have a go. Let's whip through these fairly quickly so you bring your skills up. Now the important thing here is not to be frightened by these sorts of expressions. Remember the rule, you have to multiply the exponents together. So don't forget to multiply all of x plus 1 by 2. I'll give you a hint, it's not the answer 2 to the 2x plus 1. It's different from that. Okay, so pause it, have a go, and I'll show you the answers now. Alright, so there's some answers for you. Make sure you get these, because in models of growth we are wanting to describe all different situations, and pronumerals, letters instead of numbers, will be around the place quite a bit. Okay, let's look at another example and keep building up the skills. Only got a few things here. Now this is getting a bit messy. Some negative exponents with positives, and you've got to write it without negative indices. So okay, the first thing you might do is this negative exponent means 1 over. So it goes in the bottom line. Now this negative exponent means 1 over, it will change lines as well. Let's look at that. That sounded like a very basic monkey see, monkey do type rule, didn't it? So let's have a look at this. Let's look at the c to the neg 1. Forget the top line for the moment. What's this really mean? 1 over c. and when you are dividing by a fraction, you invert and multiply. I wonder if you can explain why that works. So see that? The C, see? That C set there, see it? It goes in the top line. Okay, why? Because of this idea. If it's in the denominator and it's got a negative power, it means 1 over, and dividing by a fraction inverts and multiplies. Okay, so here we are. There's the explanation there. Okay, so just unpack that, make sure. Come and practice some with the negative exponents now, or indices. Okay, just make sure you combine all your rules. You've got to square everything in there. So everyone's power inside the bracket must be multiplied by 2, because we're using this rule, only there's a big complicated A in there, isn't there? There's several terms in here, not just one. So when you multiply the powers for the A to the M to the N rule, you've got to do it to everything inside the bracket. Okay, good luck with that. Let's have a look at the answers. Okay, so how are you feeling with all this revision of exponents, excuse me? It goes back a few years, doesn't it? Okay, let's go on and have a look. And let me just get that right. Yep, here we go. All right, without using a calculator, write in simplest rational form. So we're getting into these rational exponents or fractions in the exponent. So let's have a look. So you could break 8 down to 2 cubes, all to the 4 on 3, and then that would cancel. So it becomes 2 to the 4, right, showing the cancelling there, and that's 16. I want to show you another way of doing that problem. You could go like this: 8 to the 4 on 3 equals 8 to the 1/3 all to the 4th. And 8 to the 1/3, the cube root of 8 is 2. 2 to the 4th is 16. I think this way sort of reinforces in your mind that 8 to the 1/3 is the cube root of 8, whereas over here you're just cancelling the powers. See that? Cancelling the indices. And you don't really have to hesitate to and stop and think that means the cube root. Okay, so think about whichever way you want to do it here. 27 to the -2 on 3. They have suggested you put 3 cubed to the -2 on 3, then cancelling 3 to the -2 is 1 on 9. You could do that differently. I generally like people to say negative exponent first. 27, so it's negative is 1 on, which is 1 on the cube root of 27 all squared. And that is cube root 27 is 3, 1 on 3 squared is a 9th. So it's a similar number of steps, so one solution is as good as another. Remember, mathematical solutions are deemed to be best if they are shortest. Okay, so whichever way you want to do it, just make sure you can go through the steps and get the correct answer there. Okay, I'll give you some to practice now with these rational powers, and I think this is our last set now. So whichever way you want to do it, okay, have a go, and I'll show you the answers now. All right, there they are. Right, well, I hope you're able to get some of those right, because they're important in working with these exponential functions. There's lots of things we want to do with them. Anyway, I will catch you in another presentation shortly, because this gets very exciting, so stay with it. Cheers for now.